All right. So, what we're going to do today, and we're going to start it today and probably just pick it back up with after a winter break. So we got something special planned for tomorrow.
Polar Express.
Better one and done as first.
What we're going to introduce this today is the inverse trig functions. Okay? So, the inverse trigonometric functions, these are different than the six trig functions we saw. Okay? What these do is they actually undo the trig function, allowing you to solve for what theta is. Okay? So, basically, if I had a problem like the sine of theta equals 1/2, and I wanted to know what theta was, okay, I'd have to have some sort of method of undoing the sine to it. Okay? A lot of people are like, oh, why don't you just use something like the cosecant to both sides, or something like that. Well, the problem is the cosecant of the sine of theta is not equal to theta. They don't cancel each other out. In fact, the cosecant of theta times the sine of theta is 1. Okay? So they're reciprocals, but they're not inverses. Okay? So if I want to do this, I need a function, basically, to solve for theta here. I would need a function that undoes the sine. Okay? And it turns out we have such functions. Okay? They're called inverse trig functions or arc functions. Okay? And it turns out my function then, if f of x is equal to the sine of x, the inverse of it is something called the arc sine of x. Okay? And this right here is basically the inverse function for the sine. Okay? And so by definition, what these things are is the arc sine is the function where the arc sine of the sine of theta would be equal to just theta. So it is the function that undoes the sine. Okay? Likewise,
The arc sine's a button on the calculator. It's like the opposite.
yeah, the -1, that's the arc sine. Likewise, the sine of the arc sine of theta is also equal to theta. Okay? So the arc sine is a function, again, it's just a function that undoes theta. So if I wanted to solve this up here, going back to my example, okay? Our example we had up there is how do I find theta for sine of theta equals 1/2? I do the arc sine of the sine of theta and have that equal to the arc sine of 1/2. And that leaves me with theta is equal to the arc sine of 1/2. And so you get a calculator out at that point. That just throw on the floor. It's alright, these TI-30s are pretty much indestructible, yeah. Although I actually broke someone's TI-30 once. It was such a freak accident because that usually never happens.
The accident was sheared.
I like dropped it, it fell just the right way where it cracked the LCD screen. Yeah, that's normally impossible. But
Is arc sine like the sine to the negative?
yes, that's what it means on your calculator. Okay? So I'm doing the arc sine of 1/2 in radians. okay, I get that theta is 0.524 radians. So if you want that in terms of pi, you just divide the answer by pi, and then so the number you get, you put pi on it, and that's what it would be in terms of pi radians. So let me extend the page down. So actually doing that, so you can see what I mean, okay? I can write this as actually 0.167. Oh, that's 16. It's a sixth. So it should be pi over. No, not pi over 6. But anyway, this is 0.167 pi. Okay. I got that, by the way, 0.167 pi by just dividing 0.524 by pi. Okay. Actually, this thing should be able to convert that into a decimal.
Yeah.
Oops. Second. 1.6 pi. Oh, I guess that makes sense. Yeah, duh. Of course it'd be pi over 6. That's why I chose 1/2. Sorry, having a dumb moment. Just equal to pi over 6. Okay. So notice that's also something we could have figured out by looking at the unit circle. I could have looked at the unit circle to see where the sine was equal to 1/2, and would have gotten. I could have reversed it that way as well. Okay. But the arc sign is what allows us to undo things to be able to write out your answer. Okay? Just like so. So, that's what the arc sign does. Okay? There are, every trig function has a corresponding arc function that goes with it. So the sine, okay, is undone by the arc sign. Okay? The cosine is undone by the arc cosine. Okay? The tangent is undone by the arc tangent. Okay? And on top of that, even though they're very, very rarely used, okay, the cosecant, secant, and cotangent are all undone by their various ones as well. There's an arc cosecant, an arc secant, and an arc cotangent. Okay? And all those would be the functions that undo sine, cosine, tangent, cosecant, secant, and cotangent. I'm going to go ahead and just kind of highlight those in a different color. These are very rarely used.
If we would put those into the calculator, that would be 1.
Yeah, it'd be 1 over, it'd just be just like you would the same as the sine, cosine, tangent.
Okay, so 1 over.
1 over, yeah. Okay. They're very rarely used. The very few problems you'll see involving them on like a homework or a test or a quiz or something, will be ones too where you can use the unit circle to find the answer. Okay, you don't necessarily have to use a calculator because again they're so rare. Okay, but the sine, cosine, and tangent ones, these are their opposites. Okay, on a calculator. Okay, these things are represented as sine to the negative first, cosine to negative first, and tangent to negative first, like that. Okay, I've never been a huge fan of that notation. Okay, because it's misleading about what it's actually saying. Okay, so when I ever write a test or a quiz, or when I write them up on the board in class, I'm almost exclusively going to use the arc sine, arc cosine, arc tangent notation. Okay. But just realize on the calculator, they do this to save space, okay, on the calculator writing it out this way, but it's bad to think of it in terms of that because, as a warning to you all, okay, I'm going to come up here, it's like a warning. saw the sine squared of theta, that's equal to the sine of theta squared. If you saw the cosine of minus 4 theta, that'd be 1 over the cosine to the 4th of theta, which could be rewritten as the secant to the 4th of theta, okay? So normally when you have an exponent, it's just telling you to do the thing, multiply the thing by itself that many times, okay? But, maybe 2 G's, no. But, the sine minus 1 of theta is equal to the arc sine, okay? And not 1 over the sine, okay? So, that's why I don't necessarily like the notation of the sign with the -1 up there, because in every other case, the exponents mean exactly what they normally mean. But in this one particular case, it means something different, and so...
So there's no sign of -1, it's just the arc
Well,
sign.
if I was going to do sine of -1, okay, yeah, this thing is, when you see this in notation written out, it means the arc sine. It doesn't mean 1 over the sine, which is what the cosecant is.
Okay.
Okay?
Ah, okay, so they
so, yeah.
cosecant instead. Well,
Okay. But that's something to keep in mind when you see it out, because, again, if you solve cosine of -4 to the theta like so, that means basically 1 over the cosine to the 4th, which is the secant to the 4th. It's not the arc cosine times itself 4 times. Okay? So there's that ambiguity there, and that's why, warning, big red letters, be careful, because there is that problem with that, okay? But does everyone understand kind of the notation then? The inverse trigonometric function is always the arc function, okay? And that's what undoes things like that, okay? All right, let's look at another example here, okay? Let's see. I'm going to quickly put up a basic unit circle here, okay? Here's pi over 3, pi over 6, pi over 4, pi over 3, what is it, root 3 over 2, 1/2, root 2 over 2, root 2 over 2, and then 1/2, root 3 over 2, okay? So, we've got all that there, just like so, okay? Well, if I did a quick example, for example, if I asked, if you solve, for example, what's the cosine of theta is equal to 1/2, if I wanted what theta was, I'm going to use the arc cosine to both sides. Okay? And so I'm really doing the arc cosine of 1/2, okay? What happens in this case, okay, is that these guys cancel each other out, giving me just theta theta is equal to arc cosine of 1/2. And so how this would work, as far as solving is concerned, is saying, okay, where, when x is equal to 1/2, what angle goes with that? Well, here's where x is 1/2. What was the angle that went with it?
60.
60, or pi over 3, right?
Mm-hmm.
And so I would then say that theta is equal to pi over 3. So you could always come through and solve certain ones from the unit circle directly by just reversing the process we normally do. Normally I would say, okay, the cosine of pi over 3 is equal to what? I'd go to pi over 3 and just look at the x-coordinate, give me my answer that way. Here, I'm doing that backwards. I'm looking at the coordinate and then saying, okay, what is the angle then? So, is pi over 3 the only place where the cosine is equal to 1/2? No, where else is it also equal to 1/2?
Four.
Down here, right? down here at 5 pi over 3, it's also equal to 1/2. And so I could come up there and say, or 5 pi over 3. Okay? Now, if I were to enter that in the calculator, though, if I enter in arc cosine 1/2 into my calculator, I'm only going to get the one answer, pi over 3. Okay? There's a reason for that. Okay? So 1/2. Oh yeah, it's pi over 3. Okay? I get the answer 1.047, which is approximately equal to pi over 3. Okay? The reason for that, yeah, if you convert that to a decimal, it gives you pi over 3. Okay? The reason why that happens, why it only gives me the answer, it doesn't tell me that there's multiple answers, is because the arc functions, arc sine, arc cosine, arc tangent, they're only going to be defined through a certain amount of domain. Okay? They have domain restrictions. Okay? Let me give you an example of why that's the case. We look at these things graphically. Okay? Graphically speaking, if I come through and do the cosine graph, it starts right there, comes down, comes back up again, right? But does it stop at these points? No, it keeps repeating, right? So it's a wave that keeps going backwards and forwards, backwards and forwards. Well, remember, the idea behind, okay, an inverse function is I should be able to basically take my graph and rotate it along the, rotate it about the origin and get the flip of the picture. That is, the x and the y's are supposed to flip here, right? Well, what happens if I flip my x's and y's here? What am I going to end up with? Is it going to be a function? Is it? Think of it this way. My first point is going to be when y is 0, x is going to be 1. Okay, that's going to be say that location right there. You know, so on and so forth. And so I'm going to get my arc cosine graph is going to do something like that there. Well, if it repeated, what's going to happen?
It's going to go along with the y.
Does that pass the vertical line test? Nope. No. Okay? The arc sine, arc cosine, and arc tangent have domain restrictions. Because if they didn't, you would just allow them to keep repeating over and over and over again. Okay? They would cease to be functions. Okay? We can't have that happen, can we? Okay? So, it turns out, kind of graphically we can see why this is the case. It turns out that the arc sine, okay, arc cosine, and arc tangent all have limited domains.
It's pretty small.
Okay? Alright, the arc sine and arc tangent, well, actually arc tangent doesn't have a limited domain, I take that back. I'm lying about the arc tangent. Okay? Take that back.
John, maybe let's go to the bathroom.
Yes. Okay? So, the arc sine, okay, is only defined, its domain is from negative pi over 2, okay, which is strictly, negative pi over 2, which is, less than or equal to, sorry,
Pi over 2. No. Pi over
0 pi over 2. I'm trying to remember, is it less than, you know what, I have a book right here in my hands. Why am I sitting here beating myself up when I can just look at it? Okay, I mean, I'm screwing this royally up. Okay. Of course I'm screwing it up. Alright. My bad. Take it back apart. Okay, step. Okay, range. Okay, and yes, so it's from -1, it's less than or equal to x, it's less than or equal to 1, and its range is minus pi over 2, less than or equal to y is less than or equal to pi over 2. So the arc sine is only defined between -1 and 1, and it's only going to give you answers from -pi over 2 to pi over 2. Now why would that be the case? Why is it not defined everywhere? Okay? Well,
Cosine gives.
let's look at our unit circle, okay?
Can't give
It goes 180 degrees. No.
That's 180 degrees of arc, right? Okay? Pi over negative, this is negative pi over 2, positive pi over 2. What happens when I hit pi over 2? What happens to my y values? They start to do what?
Negative.
They're going to repeat, right?
Repeat.
And we're trying to avoid that from happening. We don't want them to repeat. We want them to be
Because you only want one input
right.
or one output.
One output, okay? And so if I did the, if I allowed this side of it, remember, so if I added, if I let, for example, the coordinate right here exist, okay, as well, then that means I would have two answers, okay, that could possibly give me that y, okay? So let's say, like, remember, pi over 3 up here, it's going to have the same y coordinate as 2 pi over 3, okay? And we can't have that happen, because that's one input or two outputs, pi over 3 or 2 pi over 3. So we have to limit the range in the domain, which is what we've done here. Yes?
A smaller question. Minus pi over 2, is that then the angle taken from perspective of the...
Yes.
So it's kind of inverse, because
Yeah.
that would be 3 pi over 2.
3 pi over 2, yep.
Yeah,
But
sick.
we look at it backwards, so
Okay, perfect.
for the sake of keeping it, because otherwise we would have like two broken pieces of range, and it would look weird.
Oh,
Okay.
yeah. Perfect.
Okay, our cosine. Okay. Also has limited domain. The arc cosine's domain, okay, it's going to be also from -1 to 1, but its range is going to be from 0 to pi this time, okay? Because remember, the cosine starts right here as x equals 1, and ends over here with x being -1. So it's going to return values from 0, increasing until I get around to pi, and then that's when it repeats. So we stick with that. So I can think of it two different ways here. Sorry, this is a little confusing. We'll see some. We'll clean it up here in a second. But basically, the arc sine, okay, is defined for that semicircle. Okay, that's the arc sine. Okay, the arc cosine. Oops, do that. Is defined on that semicircle. Okay. All right, and the arc tangent is interesting. Okay, because if I draw the tangent graph and turn it on its side, does it run into the same problem that these guys run into?
No.
No. Okay. Arc tangent, in fact, is defined everywhere. However, it can't get any higher than pi over 2 or any lower than -pi over 2. Okay? So if I came up here with the arc tangent, its domain is all real numbers. Okay? But its range is from -pi over 2 less than y less than pi over 2. And note, it's not equal to. Why is that the case? On the tangent graph, what are pi over 2 and -pi over 2? They are what?
1. Less zeros.
The
Asymptotes. They're asymptotes. So here, they're kind of asymptotes again, but they're horizontal this time. And the tangent function will never actually equal them. Okay? So, if you went through, if I took my calculator here, okay, and said, calculator, tell me what the arc sine of 2 is, my calculator is going to come back and says, I can't do that. Because 2, it says domain error, 2 is bigger than -1 to 1. Okay? My answer has to be between -1 and 1. Okay? Likewise, if I came down here for, if I tried to do the same thing with the cosine, it wouldn't work. So if I did like the cosine, clear, if I said, what's the cosine, whoa, go away. If I said, what's the arc cosine of -6? Again, domain error, doesn't work for me, okay? And lastly, no matter how hard I try, I'm never going to get an answer from my arctangent that's greater than pi over 2 or less than negative pi over 2. Okay. Everyone got that? All right. Yeah, these are this can be kind of confusing at first to get used to. Okay, but they have limited domains. Okay. Now let's go ahead and look at the graphs of all these things. We started to do that before, but let's go ahead and look at them again. Okay. So we'll start off with the graph of the arcsine. Okay. Okay. Now the arcsine, remember, its domain is from -1 to 1. So here's where -1 is. Here's where 1 is. Okay. The arcsine of -1, okay, would correspond to negative pi over 2 on my graph. Okay. So negative pi over 2, that's about 1.5. So there's 1. We'll say this right here is pi over 2. Negative pi over 2. Okay. So it starts out here like so. Okay. -1, negative pi over 2. At 1 we go up to pi over 2, so there's 1. We'll call that pi over 2. Okay. So we're at that point right there. 1, pi over 2. What would the arcsine of 0 be? What's the sine of 0?
0.
0. So the arcsine of 0 should be
0.
also 0. So that's where the thing has a 0. Okay? And we can kind of come through here and add more points if we want to. Like if I put, for example, 1/2, well, the sine of theta, we're looking for what theta makes the sine of theta equal to 1/2. And we saw it before, it was pi over 6. Okay? So pi over 6 is about right there. Okay? It'd be mirrored over here. -1/2, negative pi over 6. We go through other points like that, but it should come out to be, oh, I can do better than that drawing wise. Hang on. Okay. Should come out to be a curve that looks something like that there. Okay. So kind of like a windmill blade almost, but really it ends. So it doesn't keep going up in either direction. It just ends like that. Okay. But that would be a graph of the arcsine. Okay. Any questions there? Okay. And notice all I'm doing is flipping what I'm used to. Normally I would say this theta gives me this point here. Now I'm saying this point gives me this theta here. Okay. If that makes any sense. Okay. But there's your arcsine. Your arc cosine. Remember, its domain is also from -1 to 1, okay? But it's a little different, right? In fact, actually, these axes I drew here were not very good. This thing is never negative, okay? Because at -1, what would the cosine be? What theta gives me what angle gives me -1 when I do the cosine of that angle?
Pi over 2.
Not pi over 2.
No.
If I start at 0, when the cosine of 0 is what? It's 1, right?
Oh, yeah.
So the cosine of -1 is, if I start at 0, go around halfway the circle, I'm at what?
180.
180, which is
Pi.
pi. So at -1, we'd be up here at pi. Okay. At pi over 2 is where we would reach, is where 0 would be. So when x is 0, y is pi over 2. And down here, where x is 1, y would be 0 for this thing. And so we get a graph that looks something like that. If I think that's drawn correctly. Could be slightly off with the drawing. But you get the general idea, okay? Again, sandwich up. Actually, I did curve that wrong. Sorry. Shoot, go away. Undo. I should curve it like that. There we go. That's a better curve. Okay? Alright, so those are the two big, so it looks, again, very much like the arcsine graph, but it's been flipped and moved upwards, okay? Which, when you think about it, what did the cosine do? It was nudged over, right, from the sine? So this graph is nudged over. It almost as if I took that snippet of the graph and just snipped those two at different spots, okay? But those are those graphs there. Any questions? Again, you find them by just sort of doing the opposite of what you're doing, where you're usual. We also have a graph for the arctangent, okay? Okay, remember its domain is all real numbers, but its range is from negative pi over 2 to pi over 2. So if I were to graph it, okay,
It would be super long.
it's going to go everywhere. But at pi over 2, I have a horizontal asymptote, and at negative pi over 2, I have a horizontal asymptote. Okay, so that's pi over 2, and this is negative pi over 2. And this graph here hugs the asymptote, comes in, crosses, and comes out like so. So it's that tangent graph, okay, rotated around, okay, that we saw before, okay? But that's your arctangent graph right there. This would be the point 0, 0. When it's 1 right here, or negative 1, this would be the point, this would be pi over 4. It's not pi over 4, it's pi 4, okay? And down here, negative 1, negative pi over 4, okay? Like so, it just keeps going and going and going, okay? All right, everyone see that one? So this one doesn't end, okay? And again, that's because I could have the values get bigger and bigger and bigger as I get, but they'll never reach pi over 2, if you will, okay? All right, any questions so far? Yeah, this is kind of a lot to soak in and make sure you've got, so. Okay, take a second. Before we do some examples. Yeah?
So wait, if we were to graph both tangent and arctangent in the same graphing window, would that provide us with, is that important and significant in a way?
I mean, it'd be just kind of useful to see how the two are inverses.
Okay.
Okay? So, for example, bring it up. Come on. Give it to me.
Maybe it takes too long to do.
Yeah, but this is fine. Oh, let's take a look. Okay. Bring up the graph utility. And we could graph them together and you can see how it works. Hit the thing. There it goes. Okay. We'll zoom in one here. Okay. All right. So, tangent of x is on there.
Yeah, but
Okay. And arctangent of x is on there. And for the heck of it, I'll do a third one right there. And so if you can see here, okay, notice how the line y equals x fits perfectly between the tangent of x graph and the arctangent of x graph, okay?
Mhm.
And if I zoom this out, okay, notice how the tangent repeats, because we know the tangent repeats, but the arctangent stays long and curved. It doesn't actually ever get any bigger than what it gets, okay? It's very confined, okay? Confined in relation to the tangent graph, okay? Alright, by the way, we could do this for all our graphs, okay?
But wait, where it crosses, that has no significance at all, right?
What, 0, 0?
No, I mean like every time.
Oh, no.
Alright, okay.
Yeah, that doesn't matter, because again, these are just, I mean, they're gonna cross at just
Random points.
random points, yeah.
Ah, okay, perfect. Nice.
As the arctangent slowly approaches pi over 2.
Ah,
Okay.
thank you.
But if we look at this, the other two as well, let's do cosine. Do the sine of x. Sine of x. Notice the arc sine ends very abruptly.
That's pretty.
Okay? It doesn't actually go any further than that. And that's it. That's the entirety of the arcsine graph. So arcsine is a very small graph, isn't it? Okay? It gets all of its business done very quickly. But again, it's hugging and mimicking what the sine does. If I did cosine, you'd see the same thing. Okay? And look how that one starts at 1, okay, and curves around like so. So it, again, does a different curvy sort of thing, okay, than what my cosine does. Because it's snipping out a different section of the graph, okay? Our cosine is snipping out the portion of this graph from right here to right there, okay, to get that picture, while the arc sine was snipping it out from like right here to right here, okay, and getting a picture that way, okay? By the way, if you wanted to, just for the fun of it, okay, we come through here, and I've not seen this one in a long time, but if you wanted to for fun, let's see if it'll do it.
Oh, right.
It might get mad at me.
Oh my god, this is
Oh,
so hard to memorize. Lexius Pegasus.
no, doesn't look like it can do our secret. Yeah, I can. There we go.
So, what?
There's your arc secant.
What?
It took some finagling to do. Well, remember, okay, this thing is going to only do a partial snippet. It's doing the first snippet of the secant here. Okay.
So the asymptotes are 1 and -1, right?
So it has 1 and -1, but it's got an asymptote right here at, actually it's at pi over 2, because if I zoomed out, okay. Okay, remember, this guy has asymptotes at every pi over 2. It's got an asymptote right there at pi over 2. Okay, so it's looking at the clip of it from this section here and that section there. That's what it's doing. Okay, give you that cool looking. It almost looks like 2 of those hooks they use on stages, like stage crooks, to pull it out. If I did the arc cosine, sorry, if I did the arc cosecant, I would get another funky picture in the arc cotangent. Actually, arc cotangent will look very much like the tangent does. Okay, but you can get those kind of crazy graphs there. Okay.
Yeah, this looks funny.
Yeah, they look strange. This is more just for the heck of doing it.
Yeah, yeah.
Because again, we're not going to really have anything to do with these guys right here. Okay. All right. Any questions about how any of this stuff works? Okay. When we come back from Christmas break, we're going to be playing around more with it. Okay, getting more. What are we doing tomorrow? Yeah. I got something special planned for tomorrow.
Nice.
Let's see. Okay.
Mike, can you give a pack of balls?
Yeah.
Jake, are you feeling it now?